Hi, welcome to our pre-calculus. The topic today is composition of a trigonometric function with its inverse trigonometric function, problem type 1. So I have the header from the previous lecture here because we are going to use it. We talked about arcsine, arccosine, arctangent last time, and these pictures are from that lecture. We need to know this material very well before we get started here. So you remember that we said sine, cosine, tangent. In fact, all the trig functions have the issue that they do not have an inverse. They don't pass the horizontal line test, and officially speaking, they don't have an inverse. We sort of hacked an inverse for them by restricting them in their domain, and then created what was arcsine, arccosine, arctangent. Now, the questions that we are going to look today, let's take a look at some of these things. So, combination of a trig function with its inverse. So here you see, for example, arc cosine of 5 pi third. So two functions are acting on each other, and these are the trig function and its inverse. So this is an example, and we have several examples like that. Here's regarding tangent, regarding sine, cosine again. This is in the opposite order. Sine is on the outside, arcsine is on the inside. So that's the flavor of the questions that we are facing here. Now, an observing student is going to say, well, at the very beginning of a semester, when we looked at functions and their inverses, we had a very basic identity that if you start with a function applied to a value, and then you apply the inverse function to it, then you go back to the original. So if you have a function, you apply it to an input argument f of x, and then you apply f inverse to all of this, you go back to x. And same way with the other arrangement, that also ends up with x. So if the starting and ending values are just the same, why do we even have a discussion here? Like if you're applying arccosine to cosine, well, the output should be just 5 pi third. Why do we have a section and discussion here? Well, let me briefly mention and then come back to the issue later on that this is good when f actually has an inverse. So this is applicable if f has inverse, and we call that inverse, well, f inverse. But as we mentioned, sine, cosine, tangent, and all the trig functions, they suffer from the malady that they don't have an inverse. So we kind of created something on the side to work with, and the result of that is the complication we see here. Let me mention that you more than likely have seen this thing in your algebra classes as well. Like in the very beginning algebra, you learn that if you take a number and take a square root of it and then square that, well, yes, you do end up with the number you started with. However, if you take a number, square it, and then you take square root, what do you end up with? That's what the complication is here. Do we end up with x? No, it's a bit more complicated than that. We need to be a bit more careful. If you take a number, square it, and then take a square root, we don't go back to what we started with. Rather, it all depends how we defined our square root. So that's the complication that is here. Hopefully I piqued your interest with this. Hopefully you know what the correct way of phrasing that is. But let me come to that issue later on. let's go ahead and answer a few of the questions in this section, see what the topic is about, and then we'll have room for additional discussion. So here, for problem number 1, what is arc cosine of 5 pi third? Let's go through this problem step by step. So I draw, say, the unit circle. So here's a unit circle, 5 pi third. Where is 5 pi third? It's about here. 5 pi third. This is the angle 5 pi third. How did we measure cosine? We said we drop a perpendicular, and this is what cosine of 5 pi third is. Now the question is, find the angle whose cosine is cosine of 5 pi third. Well, there are plenty of such angles. Which one of them do you want? And that is what we had here, that if you are dealing with cosine, you want to give your answer in quadrant 1 or 2. Whatever you give at the final answer for arccosine or cosine always ends up being somewhere in this, in quadrant 1 or 2. So the output has to be between 0 and pi. So the question has to be phrased like this. Sorry, what angle between 0 and pi is it whose cosine is same as cosine of 5 pi third? So what angle in, here's a restriction, 0 pi, so let's call angle alpha. In 0 pi has the property that its cosine is cosine of this angle you're looking at, 5 pi third. So what do I need to do? Well, as we said, our final answer has to be here, between 0 and pi. And to answer that, just you go straight up, and this angle, well, if you want to calculate the cosine of that, you would have ended up with the same foot here. You would have ended up with the same cosine. So we want to find that angle. Well, we can make a very simple recipe for this thing. That angle would be same as this, and to get that, all that you have to do is to subtract that from 2 pi. Take 2 pi, subtract 5 pi third, you end up with the angle pi third, and this angle here is satisfying all the requirements. Its cosine is same as cosine of 5 pi third, and it's in quadrant 1 or 2. You need to be in quadrant 1 or 2, nowhere else. So the answer is just pi third. So if our angle is between 0 and pi, well, that would be easy. That we are already done. If the angle is somewhere else, first of all, we identify how many rotations around the circles we have gone. If we have gone any, remove all of them, and then if we end up in quadrant 3 or 4, we simply subtract that from 2 pi, and then we get our correct angle. Let's go ahead and practice another one. Let me find another cosine here. Arccosine of cosine of pi third. So again, I start with this unit circle, question is, we are given an angle pi third, so pi third. The question is, find an angle between 0 and pi, so the final answer has to be between 0 and pi, such that its cosine matches cosine of pi third. The answer in this case is the easiest, because pi third is already in quadrant 1. We don't need to go search for anything else. Pi third is already my answer because that angle is already in quadrant 1, and then I am satisfied with the requirement that I need to be quadrant 1 or 2. So here the answer is easily just pi third. Let's see if we have another example of cosine to explain. Well, cosine inverse of cosine of 4 pi third. So again, where is 4 pi third? 4 pi third, where is it? This is pi plus pi third, so we have crossed here. 4 pi third is here, 4 pi third. Okay. Cosine inverse or arccosine, either of this is same as arccosine. There are two notations for this function. Sometimes they refer to its cosine inverse, sometimes as arccosine. We want to find an angle in quadrant 1 or 2 whose cosine is same as cosine of 4 pi third. So what is the cosine of 4 pi third? Cosine of any angle, we drop the perpendicular and then the distance from the origin, that's what the cosine is going to be. Well, how can we find an angle in either of these two quadrants? Just continue this line, connect to the origin. This angle would be what we are looking for, because its cosine is also this pink line here, which is same as cosine of 4 pi third. Well, what is that angle? And that angle is, let's reason it out like this. If this is an extra pi third after pi, so we have to subtract the same pi third from pi, and what we get for this angle will be 2 pi third. So what's the quick recipe? Take the given angle, subtract it from 2 pi, because you're going to now find this, just make it positive, and then that is going to be our final answer, 2 pi third. So for cosine, our recipe is the following. So if an angle is given, suppose we want to find cosine inverse of cosine of some angle x. Step 1. If you have gone around the circle so many times in either direction until you got a very large angle, add or subtract multiples of 2 pi. So step 1 is add or subtract multiples of 2 pi until we arrive at an angle in 0 and 2 pi. Step 2. If you are in quadrant 1 or 2, well, you are already got your answer. There's nothing else to do. If you are in quadrant 3 or 4, if you are either of these two quadrants, your final answer is going to be 2 pi minus the angle that you have. So if alpha is in quadrant 1 or 2, well, that's what we wanted, and we are all done. If not, if you are in quadrant 3 or 4, then 2 pi minus angle alpha is your final answer. So let's go ahead and write this thing down here. So for arc cosine of x. Step 1, write x is equal to some multiple of 2 pi plus alpha. So alpha is between 0 and 2 pi. 2, if alpha is in quadrant 1 or 2, the answer is just alpha itself. If not, if alpha is in quadrant 3 or 4, the answer is 2 pi minus alpha, and that is for the case of cosine. So let's separate this thing from now. Let's go take a look at some examples of tangent. Arctangent of 3 pi over 4. Now, if you remember, when we talked about the tangent, this is the tangent here, our final answer has to be between minus pi over 2 and pi over 2. Arctangent of a number is some angle between minus pi over 2 and pi over 2. That's how we restricted our tangent. So when we are answering the questions here, the question is what angle in quadrant, or let's write it from minus pi over 2 to pi over 2 has same tangent as 3 pi over 4. So the translation of that this formula, what is this formula talking about? This arctangent say find me an angle that is in minus pi over 2 and pi over 2, which is, as far as tangent is concerned, same as 3 pi over 4. So how do we do this? We say, let's go ahead and locate where 3 pi over 4 is. This is 3 pi over 4. What can we do to quickly see tangent of an angle? We said to quickly see tangent of an angle, draw this so-called tangent axis. From your angle, connect to origin and go until you hit. And then on this axis, what's the location of this? Well, for 3 pi 4, very easy to say the location is going to be minus 1. You remember the radius of circle is 1, and this angle is 45 degrees, so we are going to end up at minus 1 here. Now the question that arctangent asks is, okay, find me an angle in this yellow range. Okay, that was our tiebreakers. So okay, we are going to concentrate on this set of angles. Which angle here has the same tangent as the angle you just looked at? Well, there's only one. That's the great thing about it. There's only one. There's no confusion or fight over which angle to pick, and that is the angle. Now from minus pi over 2 to pi over 2, this angle has to be measured as minus pi over 4. We cannot go this way, We cannot go circle like that, because because we are insisting that the number has to be between minus pi over 2 and pi over 2. If we allow other ways of arriving, well, there would be multiple answers, and that's what we are trying to avoid. We want the function to give one answer out, and the answer here becomes minus pi over 4. Let's go ahead do another tangent. Well, this is a tangent of tangent inverse. Let's go this one. Arctangent of 11 pi over 6. So again, what angle in, okay, here's a crucial restriction. So for tangent, we are insisting that we gotta be in this range of numbers. Other things are not used by convention, and for good reason. We said we are going to stay in this range, and this range is from minus pi over 2 to pi over 2. So when we do an arctangent, we always find one of these yellow angles here that matches the number that we have in mind. So here we ask what angle in this range has the same effect as far as tangent is concerned as this 11 pi over 6. So if we go ahead and try to figure out, well, where is 11 pi over 6? 11 pi over 6. Okay, we need to be comfortable with the unit circle. 11 pi over 6 is a big angle. It goes all the way around, comes back, stops short of 2 pi. Where does it stop at? So 11 pi over 6. If I had gone one more pi over 6, I'll be back here. So this is, in fact, pi over 6. Now, I draw this for tangent. This is my tangent axis. I ask, in this range of angles which start from minus pi over 2 and goes to pi over 2, which one has the same effect as 11 pi over 6? Well, it's pi over 6, but since it's in the clockwise direction, I have to count it as negative. This angle that is going in this direction is minus pi over 6. So the final answer is minus pi over 6. So what is the procedure for tangent? Suppose an angle is given to me. So suppose I have arc tangent of, say, tangent of some angle x. Step 1, write x as 2n pi plus alpha, where alpha between 0 and 2 pi, meaning if you have a very large angle or a negative angle, large negative angle, add or subtract 2 pi's in it until it is in the first circle from 0 to 2 pi, okay, to standardize our discussion. If you are given an angle like 1000 or I don't know, minus 200, what do? You add or subtract multiples of 2 pi until your angle sits inside the first circle. Then if your angle is in quadrant 1, if your angle is in quadrant 1, alpha in quadrant 1, well, you got it made. Your final answer is just alpha. If your angle happens to be in quadrant 2, or you're in quadrant 3, if alpha is in quadrant 2 or quadrant 3, like suppose my angle was here. What do? We said we are going to come to the sorry, let me make a correction here. If alpha is just in quadrant 2, so let's try considering here's an alpha, say in quadrant 2. What angle in this yellow range has the same tangent? Well, we have to come to this side. So for example, if this alpha, say, was 120 degrees, if this alpha was, say, 120 degrees, well, how much is left here? We say, well, 60 degrees left. Now I have to come 60 degrees below the horizon. Or in radians, if this was 2 pi third, then I say what is left here is pi third, and I have to come pi third below the horizon. So what do? I take alpha and subtract pi from it, and that's going to tell me the angle in the yellow range that has the same tangent. If alpha happens to be in quadrant 3, so if I'm coming all the way up to some location in the third quadrant, that's the red angle I'm looking at now. What's the angle in this yellow range that has the same tangent? Well, I say, okay, continue this thing into the first quadrant. This angle is what you're looking for, and that has the same tangent. They both share the same tangent. Well, how can I find this angle? It's very easy to take your alpha that you had and subtract so to find this angle, we subtract pi again from alpha, and we are going to get the correct angle. So we are going to get alpha minus pi in this case as well. If our alpha is in quadrant 4, if I go around the circle, come around to this location, then we are going to do just what we did in this problem. Take alpha and subtract 2 pi from it. And that's going to bring us to the correct quadrant. So the answer in this case is going to be alpha minus 2 pi. So the final answer becomes alpha minus 2 pi. Let's go ahead, record our observation here. So once again, we go ahead and say, suppose we want arc tangent of x. To standardize things, first we find a coterminal angle with x that is in the first circle. That is, take x, add and subtract 2 and pi to it until what is left is in the first circle. Then if you are in quadrant 1, well, it is if alpha is in quadrant 1, then you got it made. The answer is just that angle. If the angle if alpha is in quadrant 2 or 3, which we are not allowing. We don't allow 2 or 3 here at quadrant 2 or quadrant 3. We have to convert. What is the recipe for conversion? We simply subtract. The answer is going to be alpha minus pi. If alpha is in quadrant 4, what do we do? Well, in that case, we subtract 2 pi from it until our angle, so the answer becomes alpha minus 2 pi. That becomes the angle in the correct range, when you subtract 2 pi, you end up in this negative range here, and you have the correct angle. Okay, now let's go ahead and do a few sine cases. So for example, sine inverse of sine of minus pi over 2. Again, discussion is the same. We start with a unit circle. The angle that is given to us is minus pi over 2. That is the angle. Well, with the sine, the restriction is same as the tangent. Let's go back here. With the sine, the range of angles that are accepted to us is from minus pi over 2 to pi over 2, inclusive of the endpoints. Well, in this particular problem we are doing, we are just at this very bottom at the minus pi over 2, and that is in acceptable range. So the answer is just the angle you started with. So in this case, see, where was I? Yeah, sorry. So minus pi over 2 is where we want it to be. So the answer is going to turn out to be just that angle minus pi over 2. So the question here is find an angle in the restricted range minus pi over 2 to pi over 2 whose sine is same as the angle that is given, sine of minus pi over 2. So in this case, the angle that is given is already in the correct range, and we don't need to do anything. The answer is just minus pi over 2. Let's find another one which is going to be a bit more interesting. Let's just make some that I didn't have any selection here. Suppose the question was sine inverse of sine of 5 pi 6. Okay, making a problem. What is sine inverse of sine of 5 pi 6? So again, question is find an angle in minus pi over 2 to pi over 2 whose sine is same as sine of 5 pi 6. Well, let's go draw this thing one more time. Where is 5 pi 6? Which quadrant is it in? Well, obviously, is pi 6 short of a pi? I'm somewhere here in quadrant 2. Here's 5 pi 6. Question is, in this range of angles from minus pi over 2 to pi over 2, which angle has the same sine? Well, how do you measure the sine? To measure the sine, we say we dropped perpendicular to the vertical axis. This is our sine axis, really. So which one of these yellow angles has the same sine? Well, continue going to the other side. This is what you're looking for. Well, what's a simple recipe for figuring that out? That angle that you're after is same as this, which is pi minus. So if this angle was alpha, this one will be pi minus alpha. So recipe we get here is that if you were in quadrant 1, well, of course you got it made, and your answer is just the angle you're at. If you are in quadrant 2, take pi, subtract from that angle alpha, and then you are you're at the angle that you want. Let's take another example. Suppose I look at sine of 7 pi 6 and I'm applying the sine inverse to this. What is sine inverse of sine of 7 pi 6? So let me finalize this answer before I progress to, so this one answer is pi 6. 7 pi 6, I draw the unit circle again. So where is my angle? 7 pi 6 is here. 7 pi 6 is at this location. I'm again looking for angles in this range. Which one of them has the same sign? Well, how do you get the sign? I go straight to vertical. This is what sine is. What angle has the same sign? I go to the other side. This is the angle I'm after. Well, what's a simple recipe given that this angle 7 pi 6 is given? How do I find this one? Same, pi minus 7 pi 6. That's going to give my location, minus pi 6. So if I'm in quadrant 3, what do? I say pi minus the angle that is given to me is going to bring me to the right range of angles. Now I'm going to be between minus pi over 2 and 0. If I was in quadrant 4, what do? So suppose I have sine of say 23 pi over 12. Sine of 23 pi over 12. Where is that? I draw this unit circle, try to figure out where I am at. 23 pi over 12. Where is that? Almost 2 pi. Somewhere here. 23 pi over 12. I figure out that I am in quadrant 4. Now I want to be in the range from minus pi over 2 to 0 instead. So what do? I take that, the angle that I have, subtract 2 pi from it to figure out this negative angle. So I have 23 pi over 12 minus 2 pi. Take common denominator 12, 23 minus 24. I get minus pi over 12. So what is sine inverse of sine of 23 pi over 12? The answer is minus pi over 12. So for the sine, we have a similar recipe here. Let's write it. If we have arc cosine, arc sine of angle x. Step 1 in all of them. First of all, you take x and you make sure it's coterminal with some angle in the first circle, so that we are standardized. We are always in the first circle from 0 to pi. If alpha is in quadrant 1, well, we got it made. Its answer is just the angle itself. If I'm in quadrant 2 or 3, so if alpha is in quadrant 2 or 3, the answer to our problem becomes pi minus alpha. And finally, if alpha is in quadrant 4, what angle is it that, sorry, so what angle is it? In this case, answer is alpha minus 2 pi. So these are for the 3 cases. Let's go ahead, practice a few more problems. Make sure we have answered all the questions that we had here. How about the other way around? What's the sine of arcsine of 1/2? Well, some numbers given, and we are finding the angle whose sine is 1/2. So this means angle in a certain range whose sine is 1/2. Then we ask, what is the sine of that angle? It sounds a little bit silly, but sine of the angle whose sine is 1/2. Well, it is just 1/2. For all trig functions, if you have that trig function and then apply it to arc, whatever that function is, of x, you just get x. So there is no issue of finding what quadrant you're in and any of that sort. So for all these cases, you can say sine of arc sine of x, any x. It doesn't have to be any famous angle or anything. It's just x. Same thing applies to all 3. Arc cosine of x is just x, and tangent of arctangent of x is x. So the issue is not as bad when the outside function is just your trig function. It becomes a lengthy process if what's on the outside is the arc function. So let's just go ahead and record this thing for future use as well. So we have the sine of arcsine of x is just x. We don't need any kind of and say similarly cosine of arc cosine of x is just x, and tangent of arctangent of x is just x. We don't need any additional work. So that was easy. Tangent of arctangent of -1. Again, here is some number. This is the angle whose tangent is -1. And then we are asking what's the tangent of that angle? Well, it's going to be -1. So when the outside function is our trig function, we got it easy in these problems. What else we have here? Arctangent of tangent of 5/3. So let's see, we can quickly answer this. What was the deal? The deal is this. So if you have an angle, how do we find the tangent of it? We said the tangent, we draw the tangent line, and then whatever angle you got, you go until you cross the tangent line, and this is the tangent of this angle. This angle and that tangent go hand in hand. Now in this case we have 5π3. What's 5π3? 5π3 comes all the way here. 5π3 comes into a 4th quadrant. So this is 5π3. So important thing is to figure out which quadrant an angle ends up at. Now you are asking what angle in this range of yellow angles gives the same intersection. Well, this angle has the same intersection as that. The only thing is that we have to measure it from minus pi over 2 to pi over 2. That is how we are going to handle this range. So where is this? Well, if this is 5 pi third, the angle left here is going to be minus pi third. This becomes minus pi third, and so on. So we said our recipe was what? If you are in quadrant 4, the angle minus 2 pi is what you are looking after here. And so the angle of the recipe was 5 pi third minus 2 pi. Well, do the subtraction. 5 pi minus 6 pi, and that is minus pi third. Tangent inverse of tangent of 7 pi 6. Again, when the inverse is on the outside, that's where all the discussion happens. So we have 7 pi 6. Where is 7 pi 6? 7 pi 6 is like 6 pi 6 and an extra. So 7 pi 6 comes to angle like this. What angle in the yellow range has the same tangent as this? What angle in this range of angles from minus pi over 2 to pi over 2 shares the same angle? Well, it's easy. You say, well, let me continue to see what is the tangent. This is the tangent of that angle, radical 3 over 3, but we don't really need to know the actual tangent. The question is, what is this? What is this angle? Well, easy. You can just subtract pi from this thing. 7 pi minus 6 pi. You end up with pi over 6, and the answer is pi over 6. And that is the recipe we mentioned here. So if we are in quadrant 3, is that right? Quadrant 3, subtract pi, is that right? Quadrant 3, this is the quadrant we are in. We subtract pi from our angle, and then we are done. That's after we make sure our angle is in the first circle. Okay, so the conversation was rather detailed. So let's review what happened. When you're doing arcsin, your final answer has to be between minus pi over 2 and pi over 2. Arccosine, you have to be between 0 and pi. Arctangent, kind of like arcsine, between minus pi over 2 and pi over 2. The endpoints are excluded. We said the difficulty that we have here is something that we had seen before. If a function has an inverse, there's no issue in applying the function to itself. But when it doesn't have an inverse, that's when all the trouble starts. So those of you who paid attention to your algebra in high school, you remember that the square root of x squared is not x, it's absolute value of x, which is it is x if x is positive. However, it's minus x if x is negative. If x is negative, the answer to square root of x squared is negative x. Okay, so if you want to write it explicitly, it's okay to write x squared is equal to x, but then you have to say if x is positive or 0. However, square root of x squared is negative of x if x itself were negative or 0. Okay, so that fine print is what is causing all of these issues here, and it was a lot more than just 2 cases for us to consider, because we have all this additional issues to consider. Let's for the final stretch, let me just mention one more time. So graph of sine of x is something like this. Oh, maybe I shouldn't have a. Let me redraw this thing because I want to draw 3 of these. So what does this graph mean? This is the graph of y is equal to sine of x. Well, if you start at an angle and find the sine, that's straightforward. So that is the sine. But if you tell me that the sine of angle is a certain value, what is the angle itself? The problem is that you have many candidates for that. That is not only this angle, but this one, excuse me, this one, this one, this one, this one. These are all possible. So even though this was our starting angle, if I ask what is the arcsine of x, you're supposed to give me this. That is, find the angle inside this restricted sign that matches to the angle that you had. That's what we are struggling with. If so what happens is that okay, this is the x that's given to you, and then arcsine of x will be this angle. You have to always refer it back to the permitted range of values. How about cosine? For cosine we have a picture like this. Graph of cosine looks like this type of a wave. Let me improve my drawing. Something like this. Hopefully you draw it better than I did. So suppose I have an angle x here, and I want to find out what is the arc cosine of x. What does that mean on picture? Well, cosine of x means this. Now we ask, in the permitted range, where does this thing happen for the first time? So we back it out to here. This is where it happens. So what do we have to do? We have to limit ourselves to the admitted range for the cosine, which is this yellow region. So we had, like, this is the x you give me, and arc cosine of x, I have to go as far as this location to duplicate that kind of cosine, and at the same time stay within the permitted range. Same issue with respect to the tangent. So for tangent we had asymptotes, so the graph looks very different. We had so we had a graph of tangent looking something like this. So if I'm given some x value, so if this is x, so this is the tangent of x, and the question is, where does this value happen for the first time? I have to back up to this location, and this is the final answer. So in this case, the x that is given is that, and arctangent of x is this. So In that case, arctangent of x turns out to be this value, and arc cosine of x turns out to be this value, and here this is arcsine of x. So you notice that the discussion was detailed, but the problems that we solved was they were straightforward. So if you have questions, please let me know. And until next visit, good luck and God bless.